Okay, welcome to the gas mixture and law of partial pressure lesson. So far we've been looking at individual gases and the properties of the individual gases. If we change, the pressure, the temperature, the volume, the amount, we were looking at just properties that would arise from that one type of gas, okay? We are now moving in within the unit to starting to mix stuff and cause reactions and so forth. So today we're not going to quite react anything, but we're just going to look at what properties arise when we do mix gases together. Okay. All right. So there's a concept here called partial pressure. It's so if you have a mixture of gas, so you have several different gases in there, there is a pressure that is exerted by each individual gas. So they call this the partial pressure. So when it's a mixture, partial pressure, gas number one exerts this much pressure, gas number two exerts this much pressure, and so forth. Okay, so partial pressure is that individual pressure. So Dalton's law of partial pressures states that in a mixture, again, we're writing non-reacting gases. So if we have a bunch of gases together that aren't reacting and having a chemical reaction, they're just floating together. They're not reacting. There is a total pressure that arises. So the way to find the total pressure is to add up all the partial pressures of the gas. So here's an example here where we have oxygen that's separate and we have nitrogen that's separate. So right now, oxygen under certain conditions here exerts 3 pascals of pressure, okay? And then nitrogen here, under the same conditions, exerts 2 pascals of pressure. So if we were to dump them together and they're not going to react, we're going to assume that they're not reacting together. They're just in a mix, just floating around together. Together, that mixture, you're going to add up the partial pressures and you're going to have a total pressure of 5 pascals. Okay, so that's what we're looking at today, just the law of partial pressures. And then it's key again with they're not reacting, and you want to make sure that when you're adding the pressures up that you're using the same units. So here I'm using pascals. I know in the past we've used kilopascals, and there's other units like millimeter, mercury, and atmosphere, and so forth. Okay, so just when you're adding them up, just make sure that you have the same units. All right, and then if you wanted to look at it from a particle theory or kinetic molecular theory perspective, so if you're looking at every individual particle here, they're going to be moving around and colliding and so forth and hitting the wall. So the wall is detecting all of those collisions, okay, and then that's how it's measuring the pressure. So so if you have, just the oxygen's doing that, you measure something. You have the nitrogen's doing that, you measure something else. But when you have a mixture, you have both contributions of oxygen and nitrogen exerting this total pressure, and that's why it's measuring 5 pascals on this meter here. Okay, so let's jump into an example here. It's a nice short lesson today. Then we'll go from there. All right, so example 1 here, we have a gas in a scuba diving tank, and so it's designed to go 30 meters. Okay, so the oxygen has, so we looked at this already when we were looking at, dissolving, dissolving gases in water and so forth, and dissolving them into your lungs and so forth. So we saw that the tank would contain oxygen, but it also has some nitrogen in it as well. So that's why we got to be careful when we go down diving that we're not coming up too quickly, because we want that nitrogen out of our bloodstream first, back into our lungs, and then we surface at the water so we can breathe out the nitrogen. Okay. All right. So we have the oxygen here. We have a partial pressure. Okay. So you can call it partial pressure of oxygen is 2.8 times 10 to the 3 kilopascals. And we have the nitrogen partial pressure. It contributes 1.1 times 4 kilopascals. Okay, so our goal here is to find what is the total total pressure in the tank. Okay, so we know that the tank is made up of both oxygen and nitrogen, so to find the total pressure, we're going to use Dalton's law of partial pressures. So all we're going to do is we add up however many. So if we had a third gas in there, we would have P3 and so forth, okay? So we just add up all the partial pressures here. So in this case here, we only have two. So I'm going to use partial pressure of oxygen and partial pressure of nitrogen in order to get our total here. Okay, so if we go through and calculate this out, so again, you're paying attention to the fact that they have the same units. Okay, otherwise you can't combine them together. You have to convert and get them to the same units. All right, so the only thing that will fail you here now is if you don't know how to enter the value, scientific notation value into your calculator, okay? So remember you're adding here. Okay, and I end up with a value of 13,800 on my calculator, okay, kilopascals. Okay, and I'm looking at the sig figs here. This 30 meters I didn't use, but this 2.8, 1.1, those are two digits. So I'm going to convert that to 1.4 times 10 to the 4 kilopascals. Okay, so therefore the total pressure in the tank is 1.4 times 10 to the 4 kilopascals. Okay, all right, and one last one, and then we're done. Okay, so we have in this example here, so we know that if the atmosphere is 21% oxygen by volume, so we know the atmosphere. Okay, the atmospheric pressure is 101.3 kilopascals. What is the pressure of the atmospheric oxygen? So we know we have, like we have the atmosphere here, and there's lots of different gases in the air. Okay, so there's nitrogen, there's oxygen, there's carbon dioxide, etc. Right? So there's lots of different gases in the air. So 21% of it, oops, what have I given? 21% is oxygen. Okay, so out of the total 100%, so say this totaled up to 100%, so 21% is oxygen. So if we happen to know that the pressure is the atmospheric pressure is 101.3 kilopascals, can you tell me what the pressure of oxygen is? Okay, so this just comes down to, it's a percentage type question. So if you know that the total is this, and 21% of this total is oxygen, how would you calculate what that percent is? So all we're just going to do here is, it's just a percent question, so we're going to take the total and multiply by the percent. Okay, so the percent O2 times the total atmospheric pressure is going to be the pressure of the oxygen. Okay, all right, so it's like you have 21%. So maybe your friend has $101.30. You get to keep 21%. So how much do you get to keep? So 21%. So we're going to convert that to a decimal and then multiply by the pressure here. Okay, and then we'll end up with, okay, so it's about 100, right? So to be accurate, 21.273 kilopascals is the pressure from oxygen, okay? So in here we have two digits, so let's go 21 kilopascals. So the pressure of atmospheric oxygen is 21 kilopascals. Okay, so we have a gas mixture is 40% xenon gas, and it has a partial pressure of 110 kilopascals. Okay, so this is the xenon gas. What is the total pressure of the gas mixture? Okay, so we know the partial pressure of a xenon. It is 110 kilopascals. We also know the percentage of xenon of this mix is 40%. Okay, so we need to figure out what is the total pressure of this mixture. Okay, I know we don't know what the other stuff is, but we know that 40% of it is xenon. Okay, so our plan here is, so again, if we take, like if we're looking at the percentage, like percentage type questions, we know that, we have xenon here. So if we think of it as like the pressure of xenon over the total pressure, okay, would be the percentage, okay, of xenon. Okay, so we would multiply it by 100 to make it the partial pressure of xenon. Okay, so again, we know xenon is one of the gases in there. We know that there's a total. If we multiply it by 100, we'll get the percentage. Okay, so that's kind of what we always do. So if you have a test, this is your score, this is the total, you multiply it by 100, and then you get your percent, your mark as a percent, right? Okay, so that's what we're doing here. Okay, so I guess I should use the word, like I should use this instead of P because P is pressure. Okay, so let's reorganize this equation. So right now we need to find the bottom, okay, the total. So let's rearrange it. So we'll get 100 out of there first. Okay, and we'll just divide it. Okay, and then we want total, so we're going to flip this whole expression on both sides. Right, and then we're going to move this over there. Okay, so we'll have the total pressure is 100 times the partial pressure of xenon divided by the percent of xenon. Okay, so again, if you preferred to, actually plugging in all the numbers here, because if you understood this, like this is the amount of xenon over the total pressure of the mixture times 100 is the percent, right? So if we know the partial pressure of xenon is 110 kilopascals, we are trying to find the total pressure here. We'd normally multiply by 100 to get the percentage, which was 40% xenon. So if you prefer to plug all the values in and then rearrange it, you can do that. So then if you do rearrange it, you'll get to this here where you will have 100, right, percent times the pressure of xenon, which is 110 kilopascals, all divided by the percentage, which is 40%. Okay, all right, so in this case here, the percents cancel out, so then we'll have a kilopascal unit. So we'll end up with 275 kilopascals. Okay, so 40% of 275 is 110 kilopascals. That's how you would find xenon, but if we're going the other way around, this is what you need to do. Okay, so this is our kind of our solve step here in our therefore statement. Okay, so the total pressure of the mixture is 275 kilopascals. Okay, so again, with these percent questions, they're kind of like your percent concentration as well, right? You always have your what your amount, your score over the total, right? Times 100 makes whatever percentage. Okay, so this is kind of the general form to use. So we have our partial pressure, our xenon partial pressure over the total of the whole mixture, that pressure, multiplied by 100, and we'll get the percentage of xenon in the mixture. Okay, so then from there, if we're missing the total, we just rearrange it, and we'll get to our total pressure here. Okay, last one. So we have the partial pressure of nitrogen. Okay, so we need to find that. If we know the total pressure of the mixture and we know the partial pressure of oxygen, so say this is a mixture of oxygen and nitrogen, what will the partial pressure for nitrogen be? Okay, so let's write down what we have. So we have the total. Okay, millimeters of mercury, and we have the partial pressure of oxygen, which is 165 millimeters of mercury, and our goal is to find the partial pressure of nitrogen. Okay, so again here we're going to use Dalton's law of partial pressures. So that means all the gases in the mixture, so we're assuming oxygen and nitrogen are in the mixture, and that's it. They will add up together to make the total pressure. Okay, so if we just need the partial pressure of nitrogen, you're just going to solve this by throwing the oxygen over here and subtracting it from the total. Okay, all right, so let's go and do that. So we get 759 millimeters of mercury. So again, I know we haven't used these units, but the main thing here is that you're using the same ones to be consistent, and then writing your answer with appropriate units. Okay, all right, so here it's 594 millimeters of mercury. Okay, so that's the partial pressure of nitrogen. Okay, all right, and that's it. So just a few different ones that you should know how to do. So practice away and then try the checkpoint. All right, so the partial pressure of nitrogen is 594 millimeters of mercury.